So hello, today we're going to continue chapter 10. We're on chapter 10. Pretty sure we're on chapter 10. I'm losing count. Chapter 10. Today we're going to continue chapter 10, which is the going into pretty in-depth chemistry. Yeah, I don't really have much else to add. Let's just jump into it. What we've been talking about is the periodic table and the periodic trends that come from the periodic table. And possibly one of the most important trends, it's actually the basis of its shape, is something called electron configuration. You see, last chapter we learned that electrons exist in quantized energy levels. Um, the thing is, didn't really go into too much detail there. We talked about the energy levels, the n, n equals 1, n equals 2, n equals 3, and so on. But really, each of those levels have kind of some sub-bands. And what happens is that each energy level has a limited amount of electrons that it can fit. And how an element reacts chemically completely depends on where those electrons are in the various energy levels. Some of this is and it's a kind of a weird idea, but yeah. Electrons line up in these energy levels, or sometimes we talk about shells. Shells are just the way to split up an energy level. And it's the reason that the periodic table has the shape it does. That there's different type of shells, some which can only hold 2 electrons, and that kind of explains these guys here. Some that can hold 6 electrons, and that explains this shape here. Some that can hold 10 electrons, and that's this piece here. Some that can hold 14 electrons, and that's this here. Now, I'm not going to go in detail of the shells because it gets really complicated. That's for a full-size chem class. But what I do want to say is that if we look at just the first 18 elements, and the first 18, aka being up until we hit those middle ones, just these guys, what we can say is that the electrons are going to have a limited amount of how many can fit in each energy level, and that each energy level only holds so many electrons. And you see, when a chemical reaction occurs, what's going to happen is the electrons furthest from the nucleus, those are the ones that react. Those are the ones that will cause all chemical reactions. And really, they're all the ones we give a shit about. All the other ones inside don't mean anything for chemistry. Now, for an atom, we call it the valence shell, the outermost shell. And the valence shell for these, really? I lost the ability to focus over here, so let's turn that off and on. The valence shell is just going to be the outermost shell. Now, as I said, this will get complicated when you get into where I hit these yellow ones in the middle. But we talked about the period before. That the period going down is period 1, period 2, period 3, period 4, and so on. Ignoring these transition elements because they're complicated. The period is actually what the valence shell is. That which energy level the outermost electrons are in at the ground state. Going back, we can excite electrons, they relax, we get photons, that whole stuff from last chapter. But in the ground state, that hydrogen and helium, their electrons are in the first, their outermost electrons are in the first energy level. Lithium, beryllium, boron, carbon, and so on, they're in the second energy level. Sodium, magnesium, aluminum, and so on, they're in the third energy level. And what it is which energy level has the outermost electrons? That is called the valence shell. And the electrons in the valence shell are called the valence electrons. And so I'm going to use this term a lot, valence electrons. It's just the outermost electrons. That if I shouldn't have pushed that so far. If I have, let's say, a carbon atom. There's the nucleus. Carbon, if I look in the periodic table, has 6 protons. It's atom number 6. It means 6 protons, 6 neutrons. And what we can see is the second row down. That's because the first row has 2 electrons, and the second energy level has 6. That's what carbon will look like. If you were comparing more to the Bohr model, once again, it's really more complicated as the cloud model. What I would say is these 2 electrons right here, we don't give a shit about them. We only care about the outermost. It has 6 valence electrons in its last valence shell. That's the idea. Now, why do we care about valence electrons? I did kind of already say this. This is what reacts. You see, everyone wants to have a full valence shell. And all atoms, their goal is to have a full valence shell. All chemical bonds and chemical reactions are just atoms doing whatever they need to have a full valence shell. That if their valence shell has any open spots, they will either take electrons from someone else, or they'll share electrons with someone else, or sometimes they'll give electrons away. I'll come back to that. So that their outermost shell, their valence shell, is full. Really, it is valence shells decide all chemical bonds. Okay. Any questions on that? No questions? Okay. Now, here's the nice thing. All we're going to care about is valence electrons. We're not going to only care about the other electrons in it. And I'll come back to how we're going to figure out valence electrons in a second. But if you have a periodic table, let's say I look at carbon. Its atomic number is the total number of electrons it has. Carbon is atomic number 6. I don't know why that yellow is a little wide. So therefore, carbon has 6 electrons. It's in the second period. So carbon, has 2 energy levels because it's on the second row. But what we care about is valence electrons. And the periodic table goes and gives us that. See, when we talk about the family names, I said they can be numbered in 2 different ways. Just numbering from left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Or with a letter or a number and a letter. Now, traditionally, it used to always be done in Roman numerals. This periodic table has both. IA, 1A. IIA, 2A. More modern ones don't use Roman numerals because who uses Roman numerals anymore? But the letter followed by an A, whether you use Roman numeral or not, that number, what that is the number of valence electrons. You see, carbon is in group 4A. Because carbon is in group 4A, that means carbon has 4 valence electrons. Nitrogen is in group 5A, it has 5 valence electrons. Oxygen is in group 6A, it has 6 valence electrons. And the thing is, everything in the family, I said, would have the same chemical properties. Well, everything in the same family has the same number of valence electrons. All atoms in group 4A have 4 valence electrons. Carbon has 4, silicon has 4, germanium has 4, tin has 4, lead has 4, fluovium has 4. If you know what family something's in, you know its valence electrons, just the name of the group. And that's going to say how it reacts. Any questions about that? Now, this gets weird for transition elements. I said before that representative elements, everything with an A is nice and simple. Transition elements, these guys here, or inner transition elements, these guys here, get complicated. So let's for now just look at the first 18 elements, aka up to argon. So that we're only looking at the ones that only have representative elements. We're ignoring the transition. For the first 18 elements, there's actually 2 different types of shells. I'm not going to get in details with shells, but let's do a quick version. There's something called an S shell, there's something called a P shell. An S shell holds 2, a P shell holds 6. You don't really need to know that. But the general idea is the different shells, so that in the shell they can either hold 2 or 2 plus 6. 2 plus 6 is 8. All elements except for hydrogen and helium, their valence shell will hold 8 electrons. Hydrogen and helium are the exception, but everyone but hydrogen and helium, their valence shell can hold 8. Hydrogen and helium, their valence shell can only hold 2. Once again, this gets into this whole SPDF thing that I don't want to get into details for. And as I said, that's the goal. Everyone's goal is to fill their shell. And if it doesn't have 8 electrons in it, unless you're hydrogen and helium, your goal is to make it to be 8. And actually, it really is to be 8 or to be 0. Because let's look at lithium, right? Lithium here has 1 electron in its valence shell. It just wants a full valence shell. If it gives away 1 electron, its next most one is full. And so everyone's goal will be to have a full valence shell, either by giving away the outermost shell because the next one in is full, or by gathering up electrons to fill it up. And so everyone's goal is to either hit 0 valence electrons or 8 valence electrons, except hydrogen or helium with 2. Once again, in the family though, in a given family, everyone has the same valence electrons. In family 1A, hydrogen has 1, lithium has 1, sodium has 1. In family 2A, beryllium has 2, magnesium has 2. And in fact, if I continue down, it would also be calcium has 2, and strontium has 2. This is why things in the same family react the same. It's because they all have the same number of valence electrons. Now, we're going to go into a lot more detail of valence electrons next chapter when we talk about chemical bonding, but that is the general idea. Any questions? Okay. That's why things in the same family have the same chemical properties. They have the same number of valence electrons. Once again, details next chapter. Another periodic trend is atomic radius. If you have a periodic table, you can figure out the relative radius between different elements. Radius just being the distance from the nucleus to the outermost electrons, aka the nucleus to the valence shell. As you go down in the periodic table, and this is just ignoring the transition elements, but it's otherwise the periodic table. When you go down, you're adding more energy levels. If you're adding more energy levels, you're adding a bigger radius. We already covered that, at least for hydrogen, that the radius is 0.053 nanometers times n squared. And so anytime you move down in the periodic table, you're going to have a bigger radius. Of note, when you go to the right on the periodic table, there is more electrons and protons. That means there's a larger force. So moving to the right on the periodic table is going to be a smaller radius. And so there's actually a periodic trend here. That radius goes up anytime you move down or to the left on the periodic table. Cesium has one of the biggest radiuses of all elements because it's down to the left. In fact, francium is even bigger because francium is down one from that. This doesn't actually show the bottom row of the table for some reason. But that's the general trend with that. Okay. Another periodic trend, ionization energy. You can always remove an electron from an element. Metals like to lose electrons. Once again, their goal is to get their valence shells to 0. But from any element, you can take away electrons. Even hydrogen with only 1, you can take its 1 sole electron and leave it lonely and alone. Keep in mind, we're going to say an electron has a charge -1, a proton has a charge +1. Really, it's 9.1 times 10 to the whatever coulombs, but we're just saying elementary charge. Anytime you remove an electron from an atom, you ionize it. What it means when you move an electron is you take it from an atom to an ion. An ion is just an atom that you change the number of electrons. And to take an electron away takes energy. There's something called ionization energy. And ionization energy is the amount of energy required to move an electron from a neutral atom in the gaseous state. Just how hard is it to do? Okay. Well, the ionization energy also follows trends. So we talked about metallic character. We said something metallic character was how readily something gave up electrons. And ionization energy is how much energy it takes to remove an electron. So the more non-metallic something it is, the less likely it is to give up an electron. Kind of makes sense they match. And that's the general idea. Ionization energy increases when you go up in a family. This is due to more energy levels, though further away from nucleus, less attracted. And ionization energy increases as you move left to right. And this just matches the metallic character. And so ionization energy also follows a periodic trend. In fact, all the trends I covered so far, here's all of them. I didn't actually talk about electron affinity. That one is not one we've covered in this class. It's more that I just, store this figure. So you could ignore electron affinity. Let's just make it say ionization energy. Or has ionization energy already. But that's the general idea. That all of these things move as a trend on the periodic table. This is individual trends. There is some things that might vary, might be some exceptions, but that's the general idea. Questions? Any questions? Okay. So that is atoms. Oh, elements. That is elements. That's everything I want to say about elements. And when I started this chapter, I said we were going to talk about 4 different things: elements, compounds, homogeneous mixture, heterogeneous mixture. So here I am, like one class and a quarter of a class through, and I've only done one of the 4 categories for this chapter. It's because the other categories aren't as complicated. Let's look at compounds a little bit. Compounds, as I said before, are just a particle consisting of 2 or more atoms chemically bonded. And I already talked about the chemical formula. I did it a little bit on Monday. Pretty sure. Yep, I did. And I said you just write how many you have of each element. The level of the element and a number saying how many. Well, you don't need to write once. So HCl is 1 hydrogen, 1 chlorine. NaCl is 1 sodium, 1 chlorine. H2O is 2 hydrogens, 1 oxygen. As I said, we did that Monday. Here's the annoying thing. Normally when I talk about these compounds, I'm not going to say things like HCl. I'll say hydrochloric acid. I won't say NaCl. I'll say sodium chloride. When we talk about a compound, you have to name it correctly. And this, I'm going to be honest, the next bit that I'm going to go through, I think is the most boring part of this entire class and the most pedantic, annoying part of this entire class. You see, there was this group called IUPAC, which stands for International Union of Pure and Applied Chemists. I personally like to think of them as a secret shadow organization, like who never have like bright lights shining, that they only see like the silhouettes of people making evil plans. But basically, they're a group of chemists who decide on the nomenclature of chemistry, aka it's their job to say how are things named. And they say exactly what we call every chemical formula. They tell us how to name things. And so this is going to say how we, why is it sodium chloride and not chloride sodium? Because IUPAC tells us so. There are some exceptions. The exceptions are all compounds that have more common names. There's actually 11 compounds with special names, and most of them are ones that people found, before chemistry. Waddle. Waddle has a different word in every language. It's because waddle was people knew what waddle was before they knew the chemistry of waddle. Same with methane, ammonia. These 11 have just special names. They don't follow the rules. But everything else will follow some set rules. And so I'm going to go through them. The first is anytime you have a compound with a metal and a non-metal. If you have a 2-element compound, which is binary means 2, And one is a metal and one is a non-metal. And keep in mind, if you want to know what a metal and a non-metal is, look at a periodic table, look at that staircase thing that I marked it on. You should be able to tell which is which. When you have a metal mixed with a non-metal, the name of the compound is the name of the metal followed by the name of the non-metal. But the end of the non-metal is changed to "ide." As in bromine becomes bromide, chlorine becomes chloride, fluorine becomes fluoride, hydrogen becomes hydride, iodine becomes iodide, and so on. And so, like if I write in front of you NaCl, sodium is Na, Cl is chlorine. That's sodium chloride. Al2O3, Al is aluminum, O is oxygen, aluminum oxide, calcium nitride, and so on. Now, this can be a little complicated if we get into some of the transition metals. Some of the transition metals, the metal piece can become more complicated, aka anything in this yellow region. But we'll come back to that next chapter. For now, let's just deal with the ones not in that region. If you have more than two elements, if there's a metal and a non-metal and something else, aka another metal, another non-metal, anytime there is more than two elements and at least one of them is a metal, if there's more than two elements and they're all non-metals, don't worry about it yet. But if there's more than two elements, at least one of them is a metal, that's going to mean there's something called a polyatomic ion is. See, an ion, as I said before, is an atom that changes the number of electrons and gains the charge. A polyatomic ion is an ion that's made up of multiple elements bonded together in a special way with a set charge. And if you ever have something with a metal, at least one metal, at least one non-metal, and more than two total elements, what it normally is it's going to be some metal combined with a polyatomic ion. Though it can also be ammonium mixed with a non-metal. I'll come back to that. If it has more than two elements, how you name it is you just say the name of the first element followed by the name of the polyatomic ion. If instead of it starts with a polyatomic ion, you just use that instead for the first one. So take, for example, ZnSO4. ZnSO4 is Zn, zinc, followed by SO4. And this table right here says SO4 is sulfate. So therefore, this is zinc sulfate. Now, I'm going to say right now, normally in chemistry class, you're going to have to memorize a lot of this shit. This is sulfate. This is sulfite. This is nitrate. This is nitrite. You're allowed open notes on everything you do for this class. Don't memorize it, but make sure you have these names with you for the final. I'm actually going to eventually show a table that has like all of them in one spot. But I'm not going to bother quite yet. I'll do it next chapter when it's more important. But that'll be your friend too. This is when the parentheses come into play. Mg, NO3, 2. Well, Mg is magnesium. NO3 is nitrate. So it's magnesium nitrate. I don't care that there's a 2 there. It's just the name of the metal, the name of the polyatomic. The one exception is if it starts with NH4. NH4 is the polyatomic ammonium. So if something starts with NH4, you just make the beginning NH4. This has NH4 and PO4. PO4 is phosphate, ammonium phosphate. Now, once again, I don't care that there's a 3. I don't care about this 3. I don't care about this 2. It doesn't enter the naming. That's because magnesium nitrate, if I tell you magnesium nitrate, we know what the chemical formula is. Magnesium nitrate must be MgNO3, 2. It can't be anything else. Why that is, we'll get to next chapter. But that's why that's all you need for the name. And this is time you have at least one metal, at least one non-metal. If it's one metal and one non-metal, the name of the metal, the name of the non-metal with "ide." If it's a metal and non-metal and something else, the name of the metal, the name of the polyatomic ion. However, if your compound has two nonmetals, aka only two nonmetals, if your compound has no metal in it, well, if your compound has no metal in it, you're going to be in one of two cases. It'll either be an organic, and that's complicated, and we are not touching on that because it's weird and no, or it'll be another binary. Binary meaning only two elements, and will consist of one nonmetal and one other nonmetal. If it consists of two nonmetals, the naming convention is you say the name of the first element followed by the name of the second element with "ide," just like a metal and a nonmetal. Except here you got to keep track of how many of each things. And there's a reason for this. Take the mixture of nitrogen and oxygen. Nitrogen and oxygen can form NO. It can also form NO2. It can also form N2O3, I'm pretty sure exists. Don't hold me to that one. But they can combine in many, many, many different ways. And so when you name a nonmetal mixed with a nonmetal, we need to actually say explicitly what all the numbers down here are, so that we can keep track of what the formula is, so we can tell the difference between those three formulas. When you have a binary with two metals, the naming system will be the name of the first metal followed by the name of the second nonmetal with "ide," and before each bit there will be a Greek prefix, except for Nona. Nona isn't Greek. I don't know why Nona got mixed in and not the Greek word for 9, but I'll say that in a second. There is an exception. You normally don't say mono. There were some versions of that. I'll come back to the exception here in a second. But here is the Greek prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. You're probably familiar with the idea of carbon dioxide. Carbon dioxide is CO2. It's carbon dioxide. That's what the di means. It means there's two oxygens. I said mono is omitted unless it requires to avoid confusion. That's carbon monoxide. Carbon monoxide is just CO. We use the mono just because carbon monoxide can kill us. Carbon dioxide we breathe out. We kind of want to make a big deal to point out which is which. But you normally don't do mono. There's only like a few special cases when you do mono. Once, just assume mono isn't used. And if it is, it'll be a special case and I'll warn you. And this will tell us exactly what a compound is. Take, for example, P4S3. P4S3 is tetraphosphorus trisulfide. It's tetraphosphorus trisulfide because a P stands for phosphorus, and S stands for sulfur, becoming sulfide. And then I just say 4 phosphoruses, 4 is tetra, 3 sulfurs, tri is 3. HCl, hydrogen chloride. No one has any subscripts, so I don't need any prefixes, and chlorine becomes chloride. CS2, carbon disulfide. IF7, iodine heptafluoride. Any questions here? In some way, the nonmetals are easier than the metals, because if I tell you you have iodine heptafluoride, you know the formula. For a metal mixed with a nonmetal, you're going to have to do some work to know the formula, which we're going to come back to next chapter. Okay. A fun, I guess, interesting thing about this, I don't know if fun's the right word, but I think amusing at least. Dihydrogen monoxide. There are multiple groups that worry about dihydrogen monoxide awareness. This website is a thing for dihydrogen monoxide. There's a Facebook group. The following things are all taken from the Facebook group. Dairy Pure advertises fresh and delicious milk, yet they pump it full of dihydrogen monoxide. Dihydrogen monoxide was the most abundant chemical found in the aftermath of the BP oil spill and can still be found throughout the Gulf of Mexico. Dihydrogen monoxide is used as radiation shield in nuclear reactors, and it's in our food. All newborn puppies are exposed to dihydrogen monoxide within the first 24 hours of being born. Someone in the room, what is dihydrogen monoxide? Anyone? Someone should be able to unmute themselves and figure it out. Come on, someone speak up. Nothing, huh? Okay. I guess not. Okay, di. Di means 2. Mon is 1. So dihydrogen is H2. Monoxide is O1. So dihydrogen monoxide is 2 hydrogens, 1 oxygen. Dihydrogen monoxide is waddle. Yeah, it's the most abundant chemical in the Gulf of Mexico. It's waddle. Of course it fucking is. Dihydrogen monoxide, as I said, is just waddle. And the fact calling waddle dihydrogen monoxide has been used many times, mostly to make people look stupid. Some of them are kind of amusing. In 2001, a staffer and a New Zealand Green Party member um, someone asked a politician if they would support a ban on dihydrogen monoxide, and without saying any more about it. And the politician responded saying they absolutely support of the campaign to ban this toxic substance. And literally just said someone said, will you ban this toxic substance? And people were like, yes, we will, without seeing what it was. Someone else in the same party did the same thing 6 years later. In 2002, a radio show mentioned that the Atlanta water system had been found contaminated for dihydrogen monoxide, and a local TV station picked it up on the scandal and did a whole report about how there was water within the water system without calling it water with dihydrogen monoxide. It's just used to make people look dumb, but it's kind of funny sometimes. This link is a whole list of different times people made someone look real stupid over this. Some of them are kind of funny. Okay. So, if you got to name a compound, check if it's one of the 11 ones with a special name, like waddle. Waddle isn't called dihydrogen monoxide, it's called waddle. If it is not one of those 11, check if it's binary. If it's not binary, you say the name of the metal and the name of the polyatomic ion. If it is binary, see if one of them's a metal. If one of them's a metal, it's the name of the metal followed by the non-metal with "ide." And if they're both non-metals instead, you say the name of the first non-metal, the name of the second non-metal with "ide," and you use the Greek prefixes. Okay? Okay. That's elements and compounds. Sorry. Yeah, that's elements and compounds. That's right. I also talked about mixtures at the beginning of this chapter, and I haven't covered them again since. So with our remaining 15 minutes, actually 16, I'm going to finally talk about mixtures. You see, elements and compounds are both pure substances. They're things that cannot be broken down except by chemical means. Mixtures can be edited physically, can be separated physically. And mixtures, as I said on Monday, come in 2 flavors: homogeneous and heterogeneous. A homogeneous mixture. Solutions are normally homogeneous. Metal alloys are normally homogeneous mixtures. Or something that they can be separated with physical means, but there's a constant property for a given sample. Air is 78% nitrogen, 21% oxygen, 0.93% argon, 0.03% carbon dioxide, 0.04% other things. That's a homogeneous mixture. It's all uniform. Different alloys of metal are homogeneous mixtures. They'll put together. Seawater is a homogeneous mixture. It's something where you can't tell where one piece begins and another one ends, and they're just shoved together. A heterogeneous mixture is one where it isn't uniform. Although alloys are homogeneous, metal ore is normally heterogeneous, because normally you have like a vein of copper mixing with a vein of iron, and they'll kind of have different ratios, making brass. And ore is normally heterogeneous, but it's something normally you can tell the difference. If you mix oil and vinegar and they separate, they'll mix, but they're kind of separating. That's a heterogeneous. If you have sand and water, that's wet. The water, sand is wet. There's water throughout it, but you can kind of tell the difference. A salad or trail mix or check mix is a heterogeneous mixture. You can see where one thing begins, another one ends. Now, when we talk about mixtures in chemistry, what we normally talk about is special types of homogeneous mixtures. We normally talk about a type of homogeneous mixture called solutions. Solutions is any time you have two things mixed together that one dissolves into the other. Let's say you're gonna make you're making Kool-Aid. You get Kool-Aid powder, you put it in water, you mix it up. That's a solution. You dissolve the powder into the water. Solution is anytime you dissolve something into another substance. And you actually dissolve, doesn't have to be into a liquid, but it normally is. You normally dissolve a solid into a liquid. We'll talk about dissolving other things into liquids in the last slide. You know, carbonated soda and carbonated beer is dissolving a gas into a liquid, but normally it's a solid into a liquid. And when we have a solution, you have two parts, the solvent and the solute. The solvent is whatever you have more of. So what does the dissolving? The solute is what is dissolved. It's whatever you have less of. If you have salt water, salt is the solute, water is the solvent. Now, in general, there's a special type of solution I'll talk about sometimes called an aqueous solution. Aqueous solution is any solution where water is the solvent. This becomes very important in chemistry, and we're going to see this a lot more in the upcoming chapters. Now, let's say you're going to go, I'm going to keep dealing with Kool-Aid. I don't know why I have Kool-Aid on the mind. I haven't made Kool-Aid in years. If you're going to be making something like Kool-Aid or iced tea or instant coffee, any of those, even if you want iced coffee, you normally don't make it cold. You normally make it hot and then let it cool down. The reason for this is let's say I'm making Kool-Aid. I got a whole thing of Kool-Aid powder and I add just like a tiny bit of water. I'm not going to dissolve the powder. I'm just going to have wet powder. There's only so much powder you can fit in a given amount of water. And this is the basis of saturation. For any solution, we can say a solution is saturated, unsaturated, or supersaturated. I'm going to come back to supersaturated. For now, let's just talk about these two. Let's say I have a solution of, I just have water, and I start adding sugar. And as I add the sugar, I mix it. The sugar will dissolve. There will come a point where I cannot add any more sugar. That if I keep adding sugar and mix it, it'll still settle on the bottom. That is called saturated. Saturated is when you have the maximum amount of solute that is possible. And then now it's sinking to the bottom and not dissolving. And it's actually a function of temperature. For dissolving a solid into a liquid, the hotter the stuff is, the more solute you can dissolve. That's why when you make Kool-Aid, the directions tell you to make it hot and then cool it down. Because if you make it hot, you can dissolve more. Good sweet tea, like if you want to go hardcore sweet tea, you like set up boiling, add a shit ton of sugar, then cool it. Because you can add more sugar when hot than when it's cold. And so saturated, it means you're at the maximum allowed. Unsaturated is anytime you have less than the maximum allowed. Just anything less. Supersaturated means you have more than the maximum allowed, which seems dumb. You can only have this much. It has more. Why? And here's the reason. you can actually cause something to be supersaturated on a bunch of conditions. The general idea, this is how rock candy is formed. That's why it shows rock candy there. Is that how the saturation point is a function of temperature. If you get water really, 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 really hot and then add as much sugar as you can and then cool it down, what's going to happen is if you saturate the sugar water at a high temperature and reduce the temperature, you move the saturation point, but you already have it dissolved and it will stay dissolved. I'll come into more detail on this in like 2 slides, but that is supersaturated. You can add more than physically possible by fucking with the temperature as you dissolve things. Now, the solubility is by definition the maximum amount of solute that dissolves in a specified volume or mass of solvent at a given temperature. If you add 30 grams of salt into 100 milliliters of water, it'll dissolve. If you add 40 grams of salt into 100 milliliters of water, some of it goes and sits on the bottom. Assuming, I don't know what temperature that assumed. It didn't actually say on that figure. Probably should have given me a temperature. That's how you tell. Now, for most everything, heat increases the interaction of solvent and solute. That means as temperature increases, solubility increases. And you can see the table to the right that sugar goes pretty heavily. Salt isn't on that table. That's dumb. But like something like that, CE. What's CE? I don't have all the elements memorized. I actually have no clue what element CE is. Well, whatever CE is. Oh, there it is. Cerium. That cerium sulfate goes the opposite direction. Some do, but not many. Now, going back to that rock candy with supersaturating. This what I'm about to show you is a bunch of pictures of when you supersaturate something, that's something really neat. If you have something supersaturated, so you heat it up, saturate it, cool it down, what will happen is that it'll stay in solution. And if you add any amount, the tiniest amount more of the substance, the whole thing will go, shit, I shouldn't be here, and it will all drop out. This is a series of pictures of supersaturated sodium acetate. And in the left, it's supersaturated. And they add just one little piece of sodium acetate. And when that one little piece drops in, the whole thing crystallizes. Here it is in the GIF slow motion. That supersaturated sodium acetate, one crystal added. The whole thing falls out of solution and crystallizes because it pops it out of the solution. It goes, oh wait, I'm supersaturated, I shouldn't be here. That's how rock candy is formed. You supersaturate sugar and water, then you take a stick or a string, the picture before it's string, put a little sugar on it, dump it in, and all of the sugar will go and crystallize around it, leaving you with a stick of sugar. Now, this does assume a solid being dissolved in a liquid. If you are instead dissolving a gas into a liquid, it changes and works differently. Think of it this way. You got a beer or you got a soda. You keep it cold, stays carbonated. Goes up to room temperature, becomes flat. Carbonated beverages are carbon dioxide dissolved in liquid. When you dissolve a gas into a liquid, the hotter the temperature, the solubility goes down. It goes opposite. Gases and liquid go the other way. This is why soda, that one comes warm, becomes flat. It's because when it gets warm, the solubility goes down. It goes the opposite way. This is incredibly important for aquatic environments. How fish breathe is by something's weird happening with my computer. How fish breathe is by they take oxygen that's dissolved in the water. Warm water fish are adapted to live with lower oxygen. Cold water fish are adapted to live in places with more oxygen. If you put a cold water fish into a warm water tank, it'll suffocate because it doesn't know how to deal with so little oxygen. You can also change the gas solubility with pressure. If you leave a soda open, even if it's cold, it will eventually go flat. The reason why is that pressure can affect how much gas you can dissolve. It goes by something called Henry's law. that the pressure of the gas right above the liquid is directly related to how much air you can shove in. I'm not going to go in detail for that, but just know they're related. Okay. Any questions on all this? I mean, if you're doing the live lectures, I really, please ask questions. They're made to be interactive.
Dr. Lars.
Yeah.
So like how you're saying about like cold water fish and warm water fish,
Yeah.
that would explain why like around me, I live in Hancock by the Delaware River, so trout fishing's like a really big thing. Yeah. And in the summertime, like fighting a trout when the weather's so hot, like it can kill them really fast because they must just get so tired out fast. So that makes sense.
Water, less oxygen. It could be, yeah, because they would have less oxygen. If the water was hot, they would have less oxygen. They would have to exert themselves.
And trout are like really cold water fish. They like to be in cold water. So they even like put bans on fishing when the weather gets too hot. The DEC will.
Huh.
So the fish won't die.
I have to admit, I actually grew up near the Delaware River too, but never thought of this. But I never thought about this in that way. I'm gonna be honest. This would definitely explain it. I don't know my biology really well though. There might be something else also going on that also could affect it. Just I know when I get hot, I don't. Wow, it's raining. I know when I get hot, I don't really want to move either. So there might be other things going on top of it, but that is probably part of it because when the water temperature goes up, there will be less oxygen in the water. There will be less oxygen from the use. So I imagine that is part of it. But as I said, I won't guarantee it's the only thing going on, just because that gets into biology. Biology's messy. I don't know my biology.
Yeah.
That's a cool fact, though. I will look that up, actually. I see if that is the reason why. Anything else? Okay, we'll stop there. Next week, I will start the next chapter. Hopefully, I'll have when the final is going to be by then. I'm kind of pissed off they haven't given me a final exam schedule yet. I will, the second I know when the final exam is, I'll be letting you guys know. I'm really kind of pissed off about this process. Otherwise, see you.